Welcome to Heated History, where we'll be talking about the hottest, the sultriest, the smokiest things to come out of history, and nothing says hot like the one thing that started it all. The Big Bang. A simple name for the most significant event in the universe. The Germans have it right though. They call it Der Urknall, which in my opinion is much cooler. Who first postulated the Big Bang Theory? Einstein? No. Planck? No. Hubble? Nope. It was first picked up by the most unlikely creature. Georges Lemaitre, a Belgian cosmologist and a Catholic priest. Lemaitre served as an artillery officer in World War I and witnessed the first poison gas attack in history. After the war, he studied theoretical physics and was ordained a priest in 1923. He became a professor in 1925 at the Catholic University of Louvain, near Brussels, and was known as a devoted and beloved teacher. He provided compelling solutions to the equations of general relativity for the case of an expanding universe in 1927, and concluded that the logical consequence of an expanding universe was that it must have originated at a finite point in time. If it was expanding, it must have been smaller in the past, when all of the universe's stuff was stuffed into a single particle, a primeval atom, as he called it. Lemaitre was uncomfortable with people mixing religious beliefs with science, and firmly partitioned these two aspects of his life. When Pope Pius XII referred to the Big Bang Theory as a scientific validation of Catholicism, Lemaitre respectfully pushed back. Quote, "As far as I can see, such a theory remains entirely outside any metaphysical or religious question. It leaves a materialist free to deny any transcendental being. For the believer, it removes any attempt at a familiarity with God. It is consonant with Isaiah speaking of the hidden God, hidden even in the beginning of the universe." The Big Bang started the party around 13.7 billion years ago. Our human brains can't really comprehend that number, so let me help you out. Let's assume the average eyelash is around 8 millimeters. Roughly speaking, 13.7 billion eyelashes lined up would go to the moon and back around 17 times. The universe didn't just poof into existence the way we see it now, though. When the universe was only about 10 to the minus 35 meters in length, its temperature was over 10 to the 32nd Celsius. Science nerds think that the four fundamental forces of the universe were either in perfect symmetry, or potentially even all combined into one fundamental force, like a pencil standing on its tip, too precarious to stay in place. Then the pencil began to tip. Gravity separated from the other fundamental forces, which remained unified, and the earliest tiny little baby particles were born. Perhaps this visual will help you understand. Electromagnetism. Weak nuclear force. Gravity. Strong nuclear force. Long ago, the four forces lived together in harmony. Then, everything changed when the Gravitation attacked. When the strong nuclear forces decided to leave the friend group, the universe had some serious soul-searching it needed to do, so it got strangely into inflation. Cosmic inflation, if you will. In this fraction of a second, the entire universe expanded about 10 to the 26th times, to about the size of a grapefruit. Those baby elementary particles from the grand Unification Epoch were now a hot, dense quark-gluon plasma soup. Say that 10 times fast. The strong nuclear forces separation from the other two caused some wild particle interactions, leading to some exotic particles like W, Z, and Higgs bosons. You can think the Higgs bosons were slapping some sense into the radiation energy flying around at this point, because they were able to force the energy to transform into mass by slowing the energy particles down. Thank you, Higgs boson. Temperatures are now cooling down to a reasonable 10 quadrillion degrees, and the four fundamental forces of electromagnetism, weak nuclear force, strong nuclear force, and gravity assumed their present forms. Quarks, electrons, and neutrinos formed in large numbers, and quarks and their antiquarks had a knife fight in the parking lot of Chili's to determine the survivors. Due to some freaky science nerd stuff, there were more quarks than antiquarks, which means that the quarks won the turf war, which would ultimately combine to form matter. The universe finally cooled down to 1 trillion degrees, which was cool enough to allow quarks to combine to form hadrons, which is a fancy nerd name for protons and neutrons. Because things were so compacted and wild, electrons slammed into protons and fused together to become neutrons. These impacts also created the massless neutrino particles, which still surf the waves of space at the speed of light. Some of the neutrons and neutrinos would collide again and recombine into proton-electron pairs. All this combining, splitting, and recombining was pretty wild, but they did at least keep to the rules of conservation of energy. Most of the hadrons and antihadrons have annihilated each other by this point. Leptons, like electrons, and antileptrons, like positrons, were the dominant mass of the universe. As these smaller particles collided and annihilated each other, energy was released in the form of photons, and then the photons started slamming into each other and creating more electron-positron pairs. Now, you may be thinking to yourself, I know some of these words. But where are the atoms? Well, we are finally at the point where the atomic nucleus can form, because the universe has finally cooled down to a pleasant 1 billion degrees. Nuclear fusion of protons and neutrons form the nuclei of simple elements like hydrogen, helium, and lithium. But then, after around 20 minutes, it's too cool for nuclear fusion to continue. Newly formed atoms don't have the happy electrons orbiting them like you may have seen in your science textbook quite yet, though. It's still far too spicy for them to settle down. What, did you think the Big Bang was basically instantaneous? Well, so did I starting this video. During this long period of cooling, the universe continued expanding, and was filled with plasma, a hot, steaming soup of atomic nuclei and electrons. Most of the energy of the universe is dominated at this point by photons, which continue to get up to freaky shenanigans with charged protons, electrons, and nuclei. The expanding universe finally cooled to around 3,000 degrees, about the same as the surface of our sun. Negative electrons were captured by positive hydrogen and helium nuclei, canceling out each other's electric charges. By the end of this period, the universe was a somewhat less messy fog of about 75% hydrogen and 25% helium, with a tiny itty-bitty amount of lithium joining the party. Once the free-flying electrons were finally laden down with the old ball and chain, the universe became transparent to light for the first time, meaning this is the earliest epoch science hippies can observe today. All of those photons which have been bouncing around, causing havoc, were finally free to travel the universe at the speed of light. They're still road-tripping through the universe in our today's cosmic background radiation. Imagine a universe without light. Atoms float through space with no stars. Matter is diffused, and activity in the universe has tailed off dramatically, with low energy levels for millions and millions of years. The universe is dominated by dark matter, which gives out no light, and does not interact with electromagnetic forces. Its only evidence of existence is inferred from gravitational effects on visible matter. There is anywhere from 6 to 7 times more dark matter as bright matter, and we still have no idea how to see this stuff. During this dark age, there's no stars, no light, and the universe is 100% completely dark. Then, clouds of hydrogen gas are slowly pulled together, causing a gravitational collapse, and then, light. A quasar is formed, the first in our universe. It's not quite a star like our sun. Instead, it derives most of its energy from the very hot matter swirling into a black hole, and can generate as much light as 100 normal galaxies. I don't know about you, but I think that's strangely motivational. Even when matter is being sucked into a crushing death by a black hole, it shines brighter than it ever has. Be a quasar. Gravity slowly pulls the primordial gas together into pockets, which become more and more dense, even as the universe continues to expand rapidly. These small, dense clouds of hydrogen and helium eventually collapse under their own gravity, forcing atoms into closer and closer contact, until they become hot enough to trigger nuclear fusion reactions, igniting the universe's first stars. The first stars were absolutely enormous, nearly 100 times larger than our sun. They didn't live for long, because the process of nuclear fusion in a star's core, at its most basic, shoves smaller elements together to make larger elements. Eventually, the elements created are too big to keep shoving together, and the star burns out and explodes into a supernova. These explosions throw the heavier elements like metals out into the universe. Large volumes of matter collapse to form galaxies, and gravitational attraction pulls galaxies together to form clusters and superclusters of galaxies. And remember, the universe is still expanding. Our solar system was formed around 4.5 to 5 billion years ago, or 8.5 to 9 billion years after the Big Bang. Our universe is still expanding, and let's hope our species survives long enough to try expanding through the stars too. Hey, thanks for watching. This is the first of what I hope to be many videos covering the hottest things in history. My brain is kind of hurting from all the science hippie ramblings I had to stuff into it to make this video, so the next video will be focusing on somewhat more recent history. Have an idea of what I should cover next? Let me know in the comments below. Leave a like and subscribe to boost my fragile ego and to get notifications for my next video. I'm thinking it's going to be hot. Very hot. Stay toasty, my friends.